All right, the next couple of videos are going to deal with dihydroxylation, which is the addition of two hydroxyl groups across the pi bond. So we see here ethylene undergoing dihydroxylation to give us ethylene glycol, which is a major component of antifreeze. Well, in this first video, we're going to look at anti-dihydroxylation, where we end up with a transdiol. And then in the next video, we'll look at syn-dihydroxylation. So anti-dihydroxylation is actually a two-step process. In the first step, we use what's called a peroxy acid. And so you might look at this formula RCO3H and say, is that a mistake or something? No, it's not a mistake. So it's very similar to a carboxylic acid, a peroxy acid. The only thing is you add one extra oxygen in here. Okay, I'll kind of squeeze it in here like that. So that's what we call peroxy acid in the first step. And once you treat your alkene with the peroxy acid, you end up with an epoxide. And so you should really just know this reaction by itself, because sometimes students will get stumped by the formation of the epoxide because they'll forget about it. Because usually we take that epoxide and then we treat it with aqueous acid and it opens up the ring and we end up with a transdiol. And so overall, it's anti-addition, right? The two hydroxyl groups are added to opposite faces of the molecule. Now, a little more information on the formation of that epoxide. I told you it's done using a peroxy acid. Two examples of peroxy acids are shown down here at the bottom. I'll just zoom in here. The peroxy acid that my students will refer to most of the time is this one here, MCPBA, which stands for metachloropperoxybenzoic acid. Again, all you have to do is write MCPBA, and that's totally fine. And then sometimes students will mention peroxyacetic acid, but I'll be honest, it usually doesn't come up a whole lot. And if you just want to write RCO3H, as is shown right here, that's totally acceptable as well. Now, I'm not going to test you on this step of the mechanism here, okay? I will not test you on this, so I'm going to remove that star, actually. I should just write here, will not ask, okay? I'm not going to ask you the mechanism for the formation of the epoxide, but it's a pretty neat mechanism here. You can see it's a total of 4 curved arrows. And then we end up with our epoxide and we liberate a carboxylic acid. But I will ask you the mechanism of the second step. And that second step is shown right here. So what's going to happen is after you form your epoxide, you're going to treat it with aqueous acid, right? Remember, the first step was RCO3H. And the second step, which is what is being covered on this slide, was what? It was just some aqueous acid, H3O+. So when we take our epoxide and we treat it with aqueous acid, as is shown here, we end up with an oxonium ion here. And what's going to happen is our nucleophile, which will be water, is going to come in and it's going to do backside attack, right? It's going to do this SN2 from the backside, which explains why we form the transdiol, why we get anti-addition. So we form this oxonium shown here, then water comes in and does a proton transfer, and there you go. So I should also point out that the epoxide can also be opened by a strong base, and that's something that we're going to look at later. But so far, we're just going to look at the mechanism of acid-catalyzed ring opening. And if you're astute, which I know you all are, you probably noticed some similarities between that protonated epoxide that you saw on the previous slide, which I called an oxonium ion, and it is a sort of oxonium. You could call it a protonated epoxide as well. You notice it's kind of like the bromonium ion, right, which is a 3-membered ring with a positive charge, right? And then you have the mercurinium ion, which we saw in the oxymercuration demercuration, which is a 3-membered ring with a positive charge as well. And so, you know, sometimes students and scientists, you know, we love to look for similarities, and you notice that all these have a strained 3-membered ring with a +1 formal charge, and all 3 of these yield anti-addition products because the nucleophile must attack from the side opposite the leaving group, just like any SN2 process. And so it's really nice to draw these parallels between the anti-dihydroxylation, the bromination or halohydrin formation, and the oxymercuration demercuration. All right, let's try a practice problem. It says predict the products that you would get when each of the following alkenes is treated with a peroxy acid followed by aqueous acid. So in step 1, we're going to treat it with our CO3H. And then step 2, we're going to treat it with H3O+. Well, since I'm your instructor, I'm going to break it down bit by bit. So let's erase some of this and let's just write out what the epoxide is going to look like. And so in this case, our epoxide is going to look like this. So I'm going to draw both of these on a wedge, which would mean our 2 methyl groups are going to be on a dash like this. Then after the second step, with our hydronium, we're going to crack that ring open and we're going to end up with a trans diol, so anti-addition. Oops, drawing a 5-membered ring there. So one hydroxyl is going to be pointing up and the other one's going to be pointing down, which means that this methyl group must be up and this methyl group must be down, and we're going to get the enantiomer as well in this case. And in the next one, let's just do this one a little bit faster maybe. We'll put here step 1, our CO3H, our peroxy acid. Step 2, H3O+. So remember, we get anti-addition, and so we'll draw our 6-membered ring. If the iPad will let me. There we go. Oops. Can do better than that. There we go. So we're going to have one hydroxyl group pointing down. The other one's going to be pointing up. And so if the hydroxyl group on the top is pointing down, that would mean the methyl group has to be pointing up. And then we're going to get the enantiomer of this compound as well.